Hello, and welcome to Europractice's webinar series on silicon photonics. I'm Ramzi Salim from Tyndall National Institute, part of Europractice services, where we work on the full range of silicon photonics from design to fabrication, advanced packaging, and system integration. Before we begin our talk today, let me remind you that you can ask questions by using the Q&A button at the bottom of the screen. After the keynote talk, we'll have a dedicated Q&A session to answer your questions. Today, you'll hear about Imec's frontiers in silicon photonics and silicon nitride. Later on, I'll tell you how you can access them through Europractice services. More precisely, through contacting Adil Masoud at Imec, who are one of our fellow Europractice partners. In fact, Adil is a project leader at Imec, who specializes in photonic integrated circuits with experience in semiconductor microfabrication and design. He's one of the coordinators for Imec's silicon nitride MPW services. Hello, Adil. Thank you very much for joining us today.
Hello, Ramsey. Thanks a lot for a nice introduction. And I believe I can share my screen now.
Yeah, it's great to have you here. I'll hand over to you so you can share your screen. So you should have access now to it. So there's a green arrow. You just want to share screen there. Perfect.
Yes. Just a system check. I hope my voice is coming loud and clear.
Yeah, nice and clear. We can see your screen. It's perfect. Thank you so much.
Okay. Yeah. Once again, thank you for introducing and also organizing this whole webinar series. Let's get directly to the point and start from the very title of this webinar. So I didn't want it to keep this the title fancy in any way, but if you think of it, photonics is such a field whose applications are really exploding in all different kind of domains, and it's very difficult to choose one application over another. Life, sensing, and interconnect might sound dramatic, but that pretty much covers large aspects of what we can do with photonics. Now, before we move further, I will just give a general disclaimer that there's a lot which is happening in photonics at Imec. What I will keep, my main focus of this webinar will be to just focus on the services of Imec, which are available through Europractice, mainly through multi-project wafer runs. But we cannot really decouple all the R&D work, so here and there I will touch the larger platform also. And we have very little time, so I'll just tangentially go through the things. If there are more questions, then we can, of course, get in touch and discuss further. So a couple of quick slides about Imec and what exactly it is. It is important to put it in the context that Imec is located in Belgium, in Leuven, which just a couple of weeks ago was selected as a European Capital of Innovation. It's a big honor because it's the city where I live in and work at. So I had to put it in the slide. But then there are many high-tech companies located around Leuven, which has helped us to get this title. And this is just a bird's eye view of Imec. Nothing to brag about the infrastructure, but just to show that if you look at different kind of larger research which is happening, you can already see a pattern that there is a 200 mm clean room, 300 mm clean room. Here, 200 mm, 300 mm means the wafer size of which CMOS technology works on. And a different kind of research, whether it is neuroelectronic, organic solar cell, energy related, all of them are largely focused around microfabrication technologies. So one of the mantra at Imec is to miniaturize things and see the power of little things, small things. And that remains the drive to pretty much establish all kind of research at Imec. It has a large clean room area, more than 4,000 researchers from around the world. And most or equally importantly, very diverse type of partners, ranging from academia to research institute and different companies. So that makes Imec in a very unique position to um, remain indulged in different kind of cutting edge technologies related with microfabrication. Now, application domains of Imec ranges from health to mobility, smart cities, industries, smart energy, but all these domains are basically based on its semiconductor and system technologies, which are based on microfabrication, what we have been talking about, and also digital technologies, a more software part of technological development. Now, all these things are becoming increasingly converged and mixed, very difficult to decouple. So let's just narrow down our focus and go to what is relevant to us, which is core CMOS technology. As I mentioned, that Imec has 2 clean rooms where most of the CMOS technology based research happens on 200 millimeter diameter wafers or 300 millimeter diameter wafers. And that really is the core part of Imec research, which is used for silicon and silicon nitride photonics development. Now, in the previous webinars, including the one where Ramzi introduced that how microfabrication is industry and the whole infrastructure is a very nice vessel where photonics research can piggyback and use the existing infrastructure to miniaturize photonics circuit. So pretty much same thing happening at Imec. Now, of course, the processing is wafer level, but what multi-project wafer? I assume most of you are familiar with that concept, but still, it's a Europractice webinar. So just a quick note that any wafer level processing happens with step and scan process, where same designs are patterned over and over again. And if that mask area can be shared by multiple designers, then it really reduces the cost. Because anyone from microfabrication industry will tell you that one of the biggest cost which comes in fabrication is, provided the infrastructure is already at place, is actually the mask technology. And if you are sharing the mask space, you reduce the cost. It reduces the cost compared to a dedicated run. But then, of course, you have smaller area to design and fewer chips to get. But this smaller design and fewer chips are usually good enough for prototyping. And it really reduces your cost from at least to 1/10, sometime 1/15 of what you would have invested in a dedicated run. Semiconductor industry is expensive, and innovating in it is also expensive. So the way I see it, this multi-project wafer concept really is a step towards democratization of innovation, where research groups or smaller companies with less fund can still gain access to really cutting edge technology. Be it any foundry, and the fact that there are so many different kind of foundries with different technologies, that really makes accessing this technology quite easier. So I had to say a lot about MPW. It's pretty much my bread and butter. So excuse me if I have gone way too deeper into that. But let's come to what CMOS technology at Imec does for silicon and silicon nitride photonics. Now, waveguides are basically just wires surrounded by a low index contrast material, as shown in this image. But so that means that if we use the same ways which are used in CMOS technology to etch a wafer or make different kind of topology on the surface, we can make these waveguides. And that's what happens. And once you make one kind of waveguide, like shown here, an optical wire, if you may, where the top surface is actually air and bottom surface is actually silicon dioxide, where this, let me get, if I can get a pointer or something.
Mm-hmm. Yes, so at the top of the screen, you'll find there is where your view options are. There's drawing elements you can draw there with.
I'm using it through my browser, so it doesn't look like I have that option.
Okay, well, kind of maybe,
But
yeah, maybe just with your mouse. We can see your mouse.
okay, so so that's an air and silicon dioxide, two low index material, which sandwiches this optical wire of silicon. So that's basically what a waveguide is. Once you can make or fabricate something like this, then sky is the limit. You can play around with all sort of designs once you have control on fabrication, and get all kind of structures, couplers, arrayed waveguides, just the pillars to fit things in, metal layers, and so on and so forth. So the very same CMOS technology can create the whole spectrum of different optical devices on it. But then the question is a constraint imposed by material. As I mentioned, this CMOS technology is largely based on silicon. So all the questions regarding contamination protocol, what material can be used with what, and so on and so forth, is largely fixed. And since we are piggybacking on this technology, we cannot really enforce our choice of material. By our, I mean the preferred choice of materials from photonics community into CMOS. So that means that the search is to find a material from CMOS industry which can do work for us. Now, photonics, we can approach by thinking like, what do we want to make, and what kind of wavelength we have to use, and then find an appropriate material for that. Yeah, sorry. So when we talk about material, just have a look at the whole spectrum, where just only part of it is visible light, and a lot of it is infrared or even higher, which are used for different things like life sciences. Visible light is amazing for life sciences. The reason we are all carbon-based life forms on this Earth, thanks to the nearest star we have, the sun. Of course, what dominates the spectrum of sun is somehow dominates our organic bodies in one way or another. And that is why, of course, there are other wavelengths also with the utility for life science related applications, but visible light dominates those kind of applications. But then for a bit of higher wavelengths, 1550 or O band and C band, that's where we have all our communication related applications. And for higher wavelengths, there are lots of applications for different kind of chemical sensing, which can be used in industry. So what materials can cover all these ranges? The materials which are transparent in this range will obviously be useful for our photonics application. Now, from the clean room, silicon, you can see that this is the transparency range for silicon, and it pretty much excludes all the visible light. So that means good enough for communication and chemical sensing and some of the bio applications as well, but a large portion is left. But if you take another material, silicon nitride, it pretty much covers the whole visible spectrum and stretches way overlaps with silicon and goes even further. So silicon nitride and silicon are obviously two good materials for all this processing. Now a question arises that if silicon nitride pretty much covers all the spectrum which is of our interest, then why think of silicon at all? First of all, if you enter into clean room, it's silicon all the way. So do not ignore that material so easily. But then again, it's a crystalline nature of silicon, which gives us even more power to manipulate it. The fact that its refractive index is way higher than silicon nitride, that means that you can make your waveguides really compact. So, and then over 40, 50 years since the inception of semiconductor industry, silicon has been treated with all sort of tests and conditioning to do this and that. Why not use that and put it for some use? So that makes a very strong case for silicon and also for silicon nitride. The fact that both of these materials are used in what is called the front end of CMOS technology, which means the very basic transistor layer, they are very well-placed materials to be used. Pretty much all the equipments in clean room can have these materials used without causing any contamination violations and so on and so forth. So silicon nitride fits the bill. The third material is silicon dioxide. It's a low refractive index material, and if you are putting it silicon and silicon nitride is wrapped around silicon dioxide, your waveguide is ready. And the good news is silicon dioxide is also heavily used in CMOS technology. So we are ready. What can we do with this thing? So let's jump more specifically to what Imec offers. Now, these are two hastily made unlabeled diagrams of silicon photonics and silicon nitride. Maybe later when I provide handouts, I can label them. But even without text, the idea here is not to give very scaled or detailed cross section or of the material stack, but give a larger idea of to compare that how CMOS technology can be used for both purposes. So typically, you start with a silicon wafer, and that is not enough. It need to have either an oxide deposition so that you can further deposit silicon nitride, or have somehow crystallized silicon on top of it, so that you can create this envelope of high index, low index contrast material for waveguiding. So as you can see in both the images, what you see, so it's not really wafer, but a slice and 3D cross section of what a section with waveguides and all would be. So what is there at the bottom is a silicon wafer, or let's say silicon substrate. Of course, it is way thicker. It's typically 600, 700 micron, while the stacks above it are just few microns, so not to scale. And then with the deposition of oxide or other materials, you can see that here, let me first focus on just what is common between these two stacks. Silicon substrate at the bottom, followed by silicon dioxide layer. And then above that, you can either have silicon nitride or silicon on top of it, which can be patterned, etched, doped, silicided, anything. And that's what makes silicon and silicon nitride stack similar. But the similarity ends there. Usually, okay, let me move to things one by one, so that I do not cause more confusion than what I have already caused. Okay, silicon nitride photonics. Going back to the stack, now we can go step by step what it has. The lowest layer is actually silicon, followed by a thin layer deposition of some anti-refractive material. That's the choice. And then oxide. After that, a silicon nitride layer is deposited. The question is that what are the ways to deposit silicon nitride? There are basically methods. You can use different kind of CVD methods, or that depends on what kind of operations or what kind of device you want to make. And with silicon nitride, there is more freedom to deposit things. In contrast to silicon photonics, where usually this layer, the waveguiding layer, which in this case is silicon nitride. In the case of silicon photonics, it used to be typically crystalline. So it's not so easy to deposit crystalline material. Maybe polycrystalline material, but not crystalline material. So silicon photonics wafers or processing usually starts on SOI wafers, or silicon on insulators, while on silicon nitride, just a deposition of silicon nitride would be enough. And after those waveguides have been patterned, further oxide can be put as this transparent box. And then different layers of metal can also be put and deposited and patterned to make different kind of electrical circuitry. Now, there can be so many different variations, as you might have seen presentations from other foundries, that silicon nitride provides you more flexibility to have layers deposited over deposited, and that makes it a very interesting material to make a very complicated 3D circuit. Here, I'm just focusing on what is offered by Imec in its BioPix platform. So, what are the main advantages of this silicon nitride photonics on CMOS technology? It's fabricated on 200mm silicon wafer. And since we are using the nodes defined by CMOS technology, it's a 180 nanometer node CMOS technology. It's not the state of the art, but then you don't want sub 5 nanometer waveguide where light won't even be confined. So when it comes to silicon nitride, which has mainly large footprint and features because of its relative low refractive index, even older technology nodes are of use, which can be used. So in the case of Imec, it is 180 nanometer CMOS technology. Even that gives quite high system compactness. Since it's a wafer level processing, that means, typically one fabrication lot contains typically 20 or 2 dozen wafers, and every wafer can have up to, depending how big is your die size, 60, 70 dies. So that means that even one fabrication run can yield you hundreds of dies, not really for device fabrication, but at least for measurement. So that means you can really control your process. You can statistically monitor it and learn from it. And that is one big benefit of using CMOS technology at wafer level, that you get a lot of data back. As you can see, I'm just giving one example, that RMS roughness, surface roughness of silicon nitride deposition. So it shows that it's like 0.28 nanometer variation, and the diagram below shows that how it's spread over the wafer. All these things which I am saying about silicon nitride is, of course, equally applicable for silicon photonics. So here I'm putting all these figures so that we don't have to come back to it and repeat the same thing. Now, the crux of silicon nitride, it's how you deposit it. Now, as I said, there are many methods to deposit it, and they allow different kind of quality of silicon nitride, and also different boundary conditions or of what can be done and what cannot be done. Let me elaborate. Now, what's the thermal budget? At what temperature are you depositing this silicon nitride? If it's a process which requires very high temperature, that means that if whatever you have fabricated before silicon nitride on your stack will probably be, wasted, will not perform very well. That puts a thermal budget. So a low temperature silicon nitride deposition gives you more flexibility to deposit, layers over layers and keep patterning. But then, of course, there is a trade-off about the quality of silicon nitride, its propagation loss, and reliability. So these are the trade-offs which you have to work on. In Imec, silicon nitride photonics platform is based on many different kind of silicon nitride deposition processes, but the one which is available through MPW offers are based on PECVD silicon nitride deposition. So it causes low wafer stress, and it allows advanced integration options. As you can see in this case, that you can see a grating coupler. This is silicon nitride layer, and beneath that layer of metal was fabricated. That means light coming from top can actually be reflected back into the couplers, increasing coupler efficiency. Again, unfortunately, this metal mirrors beneath that thing that is not yet available in MPW offers, but it is part of the platform, and that shows the advantage of PECVD silicon nitride. Now, what is available in the platform through MPW is by what we call BioPix 300 and BioPix 150. Not very imaginative names, because 300 means 300 nanometer thick silicon nitride, and 150 means 150 nanometer thick silicon nitride. Now, here is a thing. When it comes to silicon photonics and its larger applications, or let's say from where the money comes in, is mainly focused around communication. So for communication industry, there is more standardization about what wavelengths to be used. So that means that you can see a trend of how silicon photonics industry has converged on a particular thickness of silicon layer for waveguiding. So at least the thickness is fixed. What else to be done is just to pattern it, and different kind of etch depths and all. With silicon nitride, the problem is or it's not the problem with silicon nitride, but the applications of invisible light that really spans through in a very long spectrum, as I showed in a previous slide. So starting from, let's say, 400 nanometer of wavelength going up to, yeah, way larger. It can even cross mid-IR range and all. So what thickness of silicon nitride should be standardized? And the answer is that nothing, I mean, in my opinion, because if the applications are so varied, it's very difficult to fix to one thickness where eventually all foundries start making a similar kind of devices. And that is kind of a problem for MPW offerings, because when you say silicon nitride, then many different kind of players show interest, but then they might be working on very high wavelengths. Some of the applications 1000 nanometer, if they are in communication, maybe in 1300 nanometer and all, and some working on invisible range, invisible range, sorry. So that would mean for those offering MPW services for silicon nitride, will always be taking surveys, as I do, that what thickness of silicon nitride is more popular. Nevertheless, Imec offers two thicknesses, 150 nanometer and 300 nanometer, which can further be etched down to 150 and 90. These numbers largely came from a project, which was a European Union project called PICs for Life, which was probably the first major initiative in Europe to kickstart MPW services for silicon nitride. That does not mean that silicon nitride services, MPW services, did not exist before, but this particular project focused on life sciences. And that is why the wavelength range was selected as from 400 nanometer to 1000 nanometer. And the MPW processes which Imec offered, they converged on 300 nanometer thickness and 150 nanometer thickness to cover the wavelength range of 700 nanometer to 1000 nanometer in the case of 300 nanometer thick silicon nitride, and roughly 350 nanometer to 700 nanometer wavelength range for the thickness of 150 nanometer silicon nitride. And one more thing which I did not mention about this stack, if you see that there is an opening to expose this waveguide. Now, this becomes particularly important for sensing purposes. If you are making your stack, somewhere you would like your waveguide to interact directly with the material it is trying to sense. And that is also offered in BioPix platform through MPW. And then this platform has been existing for many years, but the one which is especially tailored for MPW services was validated through the 6 MPW runs in PICs for Life. So it's brand new in terms of joining an open access service, because under PICs for Life, this platform was only for early access, which means just testing the waters. Waters have been tested, and the platform is now under Europractice, offered through Europractice. So I'll here give a couple of examples from Imec about how silicon nitride photonics platform has been used. I will later on give the references where more details can be attained. But this is an interesting example where a chip-based structured illumination microscopy is used. I would see if I can run the graphics again, because it's quite cool. Yes. So what you are seeing now as a top view is a photonic circuit. Grating couplers puts light in, and a switch array distributes the light from all the directions, and the sample which is kept in this region is illuminated from all the different sides. The right-hand image, you can see an actual chip in action. Now, the details of fluorescence microscopy and all the details about how Moir patterns are used to excite fluorescence in the sample are very large. But here we can focus on how chip-based control of light can give you such a control where you can really make kind of interference patterns which are of which you really want. Like in this animation, you can see that how what is blinking red and blue are different thermal or thermo-optic heaters or thermo-optic devices, the heater layer, which I showed in the previous stack. And by controlling them, the light, which is all converging to the samples from different sides, their phases can be controlled. Hence, the sinusoidal pattern of interference on the sample can also be controlled and then selectively excite different fluorescents. And those images can further be used for fluorescent spectroscopy. Now, if this is to be done at a bulk level, will of course require lots of moving parts and very high control of things. It will be more of a mechanics than actual photonics, and that's why things going on chip makes life easier and cheaper. Well, not life cheaper, but technology cheaper for everyone. One more example from silicon nitride photonics platform is, remember I talked about that PECVD silicon nitride the thermal budget allows us to have it deposited on many things, layer over layer. So why not deposit it directly on a CMOS imager? And that's what happens here. It's a slide which I took from one of my colleague. What you see here is one of the demonstrator where when a light is made incident on a sample, usually an organic sample, it can even be your a tissue or skin. The scattered light is collimated and put directly on top of the chip. The chip in this case, as shown here, is a CMOS imager chip on which different layers of oxide, metal, and silicon nitride has been deposited and etched and patterned, including some fancy things like this copper structure, which is used as a mirror to put light in. And what happens that the illuminated light, when this chip is illuminated from the light reflected from the skin, goes down to sensors, first to the waveguides, which are usually some kind of filters, Fabry-Perot or ring resonators. And their couplers are designed to specifically go to different pixels of imager, which can be extracted during the data processing. And the whole spectrum of the light can be recreated as shown here. So different peaks for different materials exhibiting Raman effect can be a marker of what this light is bringing back from these tissues. So one of the major example is having a non-invasive sensor for diabetes, where maybe if the prototype gets smaller, maybe a wearable watch which can continuously tell your sugar level and control it, without taking the blood out. Or so this is possible and made compact because a CMOS imager can be put beneath a whole waveguide network. So waveguide do the best what they are good at, which means filter the light, spread them around, and CMOS does what it is best at by capturing this light and computing that which waveguide or which filter is emitting what kind of spectrum, what kind of pattern, and reconstruct the whole spectrum. Now to silicon photonics. This section will be shorter because a lot of advantages of CMOS technology we have already talked about. Now here again in another unlabeled cross section of silicon photonics, you can immediately see some differences from silicon nitride. To start with, this layer is actually silicon. So the processing starts on SOI wafers. It's a crystalline silicon substrate of around 700 micron thick, followed by a couple of micron of oxide, and then again 220 nanometer thick silicon layer, which is patterned at a different way. And now, at least the technology we offer for silicon nitride, we do not do much with silicon nitride in terms of doping or chemically changing it all. But with silicon, doping with silicon has been happening, since the very first chip was made, probably. So you can see that this silicon has been doped, like this colored part shows the doping layer. It can also be silicided, which means partially made into sort of a metal, which is for contacting, as shown in these vias. Germanium can also be grown epitaxially, which means that where silicon fails in capturing light, germanium can absorb it and act as a modulator or as a photodetector. So there you have things which are not transparent to light, grown on silicon and acting as an additional feature. Germanium is also a very popular CMOS technology compatible material, so there is no problem in having it integrated in the very front end of photonic circuits. What you see at the top are two layers of metal. Now, this is called the back end of a chip, and because pretty much all the things in the front end has been kept under contamination control, which means no exotic material like gold or 3,5 material has been used there. That means that whatever back-end fabrication modules are used in CMOS industry can be ported and put on top of it. Why do that? Saves a lot of development work, but more importantly, it also allows you to use a lot of packaging and assembly related infrastructure and methods which has been developed for CMOS chips to be at least partially used for photonics packaging. So that's why these are two layers of metal, of copper, and then this red big thing is many different material layer. I just oversimplified it, but that's can be a landing pad for micro bumps or connecting to be connected with the bond pads. So one more thing, you see one deep trench sort of thing here. Now that's also useful if in case you want to use a heater on top of your waveguide and keep the heat confined to that region. So the best way to insulate it is to put air around it by simply digging deep trench. Now again, a lot of more different kind of variations with CMOS technology on silicon SOI wafers are possible. What I'm showing here are what is offered through MPW services. Now, a quick highlights of Silicon Photonics platform. At Imec, Silicon Photonics is fabricated on 200 millimeter as well as 300 millimeter silicon wafers. And the two technology nodes which are used respectively are 90 nanometer. And in the case of 300 millimeter, it goes down to 14 nanometer node. With the Nesterix, what is offered through MPW is only 200 mm wafer-based technology, which means on 90 nanometer node, and it's called ISIP 50G, where ISIP stands for Imec Silicon Photonics platform with a 50 gigahertz targeted modulation. And ISIP 200 does not mean 200 gigahertz, but it means a lot more. It's a more dedicated wafer, dedicated fabrication offering. Now, what is offered through MPW? There are 3 levels of silicon patterning, which means if you see that this thickness of SOI is 220 nanometer, then it can be etched all the way, or partially down to 70 nanometer, or down to 150 nanometer. So that gives more variation in making different kind of waveguide geometries. There are 8 different kind of implant options available for silicon in silicon platform. So that means that you can really change the electrical properties and really use silicon as a semiconductor material, what it is meant to be, by doping it in many kind of different variations and acquire whatever application you are aiming for. And then there is an epitaxial germanium growth, as shown here, that allows fabrication of modulators and photodetectors. And then the backend is CMOS compatible. It is a CMOS backend basically. So that eases packaging and assembly. That's mainly Tyndall can throw better light on it, but here I will just make this claim without going into much further dispute or or questions. Another cross section for silicon photonics. Here there are more details. Again, this information is available online, and also I will provide the slides later, so there is no point of going really layer by layer. But as you can see that it has a lot more technological options for different kind of applications. Okay. A quick comparison between ICIP50G and ICIP200. Again, broadly speaking, ICIP200 provides you more customization. ICIP50G is a fixed process because it is an MPW offering, and taking part in an MPW is like ordering a pizza where there are 5 different people and they want 5 different things. So only thing you can play with is maybe different toppings at different part, but the larger base remains the same. While a dedicated fabrication run is, you have your own pizzeria, or at least an access to. So what different, okay, I might be missing a slide here, but let's continue. I wanted to elaborate more on my pizza example, but sadly that cannot be done. Now, some examples of what is made on silicon photonics platform. Here, a cross section of how a waveguide doped with different region and then contacted can actually use as in a depletion mode as a modulator, a phase shifting modulator. Now, if you put this cross section anywhere, like let's say you have designed a filter using a ring resonator where your waveguide goes couple slide in a ring. What if you change the phase, or what if you change refractive index of part of the ring? That would mean changing the phase, and hence you can modulate the light. Similar things can be achieved using a Mach-Zehnder modulator also, and that's why just this cross section. And Imec has both in its standard component library. They have a ring resonator based modulator as well as MZI based modulator. This is another example where a germanium photodetector array has been established. Now it's very interesting because what you see here in this part is a 37 channel grid of grating couplers. So 37 different grating couplers, which means that's where the light get in, and then further distributed using multimode interferometer splitters and directed towards different kind of photodetectors. Now, if you are using an optical fiber array, which can really be aligned on these different couplers, then you really have a detector which can have in this case 16 different channels, but can be more, or I think it's 37 here. So that is an example of quite a complex optical circuitry which can be put in. This is how it looks after packaging, where this is an array of fibers coming in and focusing on this. And of course, later on with the electrical connections, it can be made into a fully functioning device. Now, we are entering into the very last phase of this webinar. So a lot has been designed, fabricated, and tested over and over many years. In the case of silicon photonics, over a decade. Many of these devices work now quite reliably, which means that if you are interested only in a larger system level performance, or you're interested in developing one kind of component, let's say a very nice modulator, you don't have to worry about developing a new or designing your own grating coupler or your MMI or splitter to put the whole circuit in. What is included in a PDK, a process development kit, process design kit, are these components which can be dropped and dragged into your circuitry. And this one last slide to tell that what actually comes with a PDK. Now, of course, there are manuals and handbooks which just give which tell you the most important numbers, where to design what, things like that, which layers to be used, some information regarding technology. Design rule scripts, which can be run on different softwares, well, depends what script, to check your design, whether it is compatible with fabrication or not. Different technology settings for softwares, and a component library, which I mentioned before. Now, Imec platform, Silicon Photonics, as well as Silicon Nitride Photonics, collaborates with other Europractice members as well to offer PDK for their software. In the case of Silicon Photonics, it's available for Lucida, Synopsys, Mentor Graphics, and Lumerical. While in the case of Silicon Nitride, currently it is the PDK is available only for Lucida and Synopsys. So that pretty much covers up everything you always wanted to know about Silicon and Silicon Nitride Photonics platform and Imec. And I know it's a very brief overview, but for more detailed information, you can always approach me on this email ID. And thank you for your attention.
Thank you so much, Adil. That was very interesting. I'll share my screen here just to kind of follow up on an item here. Yeah, so thanks again, Adil. Very interesting presentation. I've got a few questions myself. But before we go into the Q&A session, let me tell you how you can access this world-leading platform through Europractice. You can visit our website, where you can find the full Imec technologies offered through Europractice. So the link's there on the top right-hand side, europractice-ic.com, with support for design and fabrication. So that kind of gives you a nice feel of what's available as well. And then on our website, you can also find the Imec NPW schedule run. Here's an example part of it for the rest of 2020. You can see here that there's one slot available for the rest of this year. So it's 14th of October, so that's next week. So if you haven't already and you're interested in submitting something, you want to submit a registration and submission by the 14th of October. And